Good afternoon, students. Welcome to the next lecture of the Dbms, Database Management Systems. Today we will discuss the deadlocks. In the last lecture, we had discussed about the transaction management, how the transactions can be managed, and we had seen different ways to manage the transaction. Today we'll study the DBMS deadlock. So first was we must be aware about that what we mean by a deadlock. So deadlock basically is a situation whenever everything is locked down and nothing can happen. For example, like in a practical situation, we are normally on a road circles and the people are all around the circles and there is no space for anybody to move. So that is the deadlock. And everybody is waiting for the other person to move back so that there will be a space. So such type of situations can be termed as the deadlock. In computation, the processes, the deadlock can also be compared with the process execution, where different processes are simultaneously in the execution, but each process is waiting for a resource that is already held by some other process. So this is the deadlock situation where no process can execute. So similarly, in the database management system, in a multi-process system, a deadlock is an unwanted situation that arises in a shared resource environment when a process indefinitely waits for the resource that is held by another process. Here is an example being given that there are multiple transactions and let's say one transaction is waiting for the other transaction to release a lock that is already occupied on some data set or some data resource, and the similarly the other transaction is also waiting for some lock to be released by the previous transaction. So both the transactions are waiting for some release of the lock and none of the transaction is releasing the lock actually. So this is not a good situation for the system, for the database, as in this case no execution can take place, no transaction can complete. So the deadlocks are to be managed carefully. These are not healthy for the system, as I have already told you. So there are ways to manage the deadlocks. One, the deadlock prevention. Deadlocks can be prevented and the deadlocks can be avoided. So first we'll study about the deadlock prevention. Now, to prevent any deadlock in a system, the DBMS has to inspect all the available transactions, all the incoming operations that are to be executed in future, and whenever the system founds that the operations can occur, can result in the deadlock, then the operations are aborted. So the operations are aborted to avoid the deadlock. But this is not always a good situation that you abort the operations, because if you will abort the operations, so there may be some tasks, there may be some programs that are left unexecuted. So it's not a very good idea, but still to prevent the deadlock situation, it is advisable to abort those tasks which may result in the deadlock in future. The other way is to let the operation wait and reoccur for after some time. So we have the different schemes for the deadlock prevention. So we have basically two schemes: wait and die scheme and wound and wait scheme. So let's study first what is a wait and die scheme. In this scheme, if a transaction request to lock a resource which is already held with some another conflicting lock by another transaction, then one of the two possibilities may occur. So which means whenever a transaction is trying to access a data which is already held by the other transaction, then these one of these two possibilities may occur. So now what is the first possibility? The first possibility is if the timestamp of the transaction is lesser, the one transaction is lesser than the timestamp which is requesting. So that means whenever the requesting timestamp is compared with the conflicting log timestamp. If it is older than the t, then the t is allowed to wait until the data item is available. So if the new transaction which is trying to access the data item is a older transaction with lot of age, then it will allow to wait until the data item is free, and once it is free, then it will be provided the access, it will be provided the data item. Now the next situation is whenever it is younger than the other transaction, then it is restarted later with a random delay but with same timestamp. So in that case, the transaction is restarted. So it's not allowed to wait, it is restarted after a delay, and then it is started from the same timestamp. So age is given preference here. So if the transaction is older, it is in execution from a longer time, then it is allowed to wait till the data item is free. And if it is younger, then it is restarted after a while, and then it is allowed to compete or fight for that data set. Now let's talk about the another scheme, that is a wound wait scheme. In this scheme, if a transaction requests to lock a resource which is already held with the conflicting lock by some another transaction, then again one of the two possibilities may occur. Now what are the two possibilities here? Whenever the timestamp of t is lesser than the other timestamps, then t forces the other transaction to be rolled back. That means t wounds the other transactions and t is restarted later with a random delay but with same timestamp. So that means here the concept of rolling back of the transaction, whenever the timestamp of the transaction is lesser than the other, then it is rolled back, and after some time it will be allowed to take the access. The second possibility, that's the opposite of the previous one. If it is not the older one, then t is forced to wait until the resource is available. Then t has to wait till the resource is available. So it is not rolled back. So it waits until the resource is available, and once the resource is available, it will provide it to the transaction. So this scheme allows the younger transaction to wait, but an older transaction to roll back. So this is the second case. And yeah, the major important case is whenever the older transaction comes and the data item is held by a younger transaction, then the older transaction forces the younger transaction to abort and release those data items. So now immediately those data items will be handed over to the older transaction and younger transaction will be rolled back. So these are the two conditions that are performed into the either of the two conditions can be performed into the wound and wait scheme. Similarity in both the schemes is that you can see the older transaction is getting the preference. So the older transaction is getting the preference in almost both the schemes. The next deadlock scheme is the deadlock avoidance. As we had already seen that aborting a transaction is not always a good idea because it may affect the system, it may affect the execution, it may affect the functionality. So we have a deadlock avoidance mechanism. Uh, in the deadlock avoidance, the mechanism, we try to detect the situation in the future where a deadlock can occur by the help of a wait for graph. So we create a graph that is known as the wait for graph, and according to the graph we try to recognize that whether there will be a deadlock in the future or not. If there is a deadlock, then we perform some requisite actions which may lead in the future to avoid the deadlock. So we need to create the wait for graph. Basically, what is a wait for graph? This is a graph for all the transactions and for all the resources. So this is a relation between transaction and resources, that which transaction is waiting for which resource or lock to be held in the future. So that is a wait for graph. It is a simple method available to track if any deadlock situation may occur in future, and it displays that the request of a transaction for the locks, and which transactions are already holding the locks, and whenever there is a release in any item, so it displays that release also. So accordingly we can create a wait for graph. So this is an example of a wait for graph, where we have the two transactions, we have a ti and we have a tj, and tj is waiting for acquiring a lock on y data set. So this is waits for lock y. tj is waiting for a lock on y wherever the ti is already holding the y. It is already holding a lock on y data set. On the other hand, you can see the ti is waiting for acquiring a lock on x data set wherever the tj, the other transaction, is already holding a lock on the x. So tj has x, a lock on x, and it wants y, and it will not release x until it gets y. Similarly, ti is holding the x, and it wants it is holding y and it wants a lock on x. So it will not release y until it will get a lock on x to complete its execution. So this is a cycle. There is a cycle, if you can see, from ti to tj and again tj to ti. There is a cycle is being made in a graph. So whenever there is a cycle, this results in a deadlock situation. And if in the graph there is no cycle, that means it is not going to be a deadlock. So with the help of the wait for graph, we can decide that in future where there will be a deadlock or not. And accordingly, the operations can be performed. So this is the wait for graph, very helpful in identifying the future deadlocks. Now what we can do is, in this let's say if we roll back, or if we deny tj to execute, once the tj is rolled back, it will release the held resources, that is y. Once the y is released, it will release x. Once the x will release, the ti will get the x, a lock on x, and it will be able to perform both the operations on x as well as on y. Once the ti is completed, it will release both the locks on x as well as on y. We can again recall the other transaction, that is tj. So now the tj can restart itself, will have both the locks on x as well as on y, and can complete its execution. So this is one way of completing the executions, where the tj operation has to suffer a delay. So but we can find that how the deadlock, or whether there is a deadlock is whether there is a deadlock in the future or not, by the help of the this wait for graph. So that's it for the lecture. The rest we'll study into the next lecture. Thank you so much.